Newton's laws of motion are a pillar of modern science. To help you understand them, let's first explore basic concepts of motion. You are probably familiar with many terms used to describe motion. Speed simply tells us how far an object will go in a certain amount of time. For example, a car traveling at a speed of 100 kilometers per hour will travel 100 kilometers in 1 hour. Velocity is the combination of speed and direction. For example, 100 kilometers per hour going due north describes a velocity. We say that an object has an acceleration if its velocity is changing in any way, whether in speed or direction or both. Note that this definition differs slightly from the way most people think of acceleration. In everyday life, we usually think of acceleration only as an increase in speed. For example, the car shown here is accelerating as its speed increases from 30 kilometers per hour to 60 kilometers per hour. But in science, we also say that this car is accelerating because its direction is changing even while its speed stays constant. And this car is also accelerating because its speed is changing even though in this case it is slowing down. One of the most important types of acceleration is that caused by gravity. When you drop an object from a tall building, it starts with a velocity of 0. After 1 second, you'll find that it will be falling with a downward velocity of about 10 meters per second. After 2 seconds, it will be falling downward at about 20 meters per second, and so on. In other words, falling objects on Earth accelerate in such a way that their downward velocity increases by about 10 meters per second with each passing second, or 10 meters per second per second. We usually write this as 10 meters per second squared. If you want to be a little more precise, the acceleration of gravity on Earth is 9.8 meters per second squared. Another crucial idea of motion is what we call momentum, defined to be an object's mass times its velocity. As discussed in more detail in your textbook, an object's momentum can change only when some overall, or net, force is acting on it. In astronomy, we are particularly interested in the special type of momentum called angular momentum, which is the momentum of an object as it turns through an angle. For example, we see that Earth has angular momentum both as a result of its rotation, which we call rotational angular momentum, and its orbit, which we call orbital angular momentum. We should also be more precise about the concept of mass, which is not quite the same thing as weight. Your mass is essentially the amount of matter in your body, while weight measures the force that your mass exerts as a result of gravity or other forces acting on you. For example, you'd weigh less on the moon due to its weaker gravity, but your mass would remain the same. We can gain further insight by thinking about a scale in an elevator. If the elevator is stationary or moving at constant velocity, the scale will show your normal weight because there are no forces besides gravity acting upon you. When the elevator accelerates up, you feel an additional force and the scale shows more than your normal weight. Downward acceleration means you will weigh a little less than normal. If the cable breaks so that you are in free fall, you and the scale would both accelerate downward at the same rate, so the scale would read 0, meaning that you would be weightless. The idea of free fall leads directly to the concept of orbit. Imagine stepping off an extremely tall tower. You'd obviously fall downward, remaining weightless until you hit the ground. Now, imagine that you ran and jumped out of the tower. You'd still fall to the ground, but because of your forward motion, you'd land a short distance away from the base of the tower. If you used a rocket and went fast enough, a very interesting thing would happen. By the time gravity had pulled you downward as far as the length of the tower, you'd already have moved far enough around Earth so that you'd no longer be going down at all. Instead, you'd be just as high above Earth as you'd been all along, but a good portion of the way around the world. In other words, you'd be falling around or orbiting the Earth. Now use this question to check your understanding. Why are astronauts and other objects weightless inside the International Space Station as it orbits Earth? Is it because there's no gravity in space, because they are in free fall, or because the space station's engines fire to balance gravity? The answer is B. They are in free fall. Just like our person using a rocket to leap off the tower with high speed, the space station's parts were all launched into space with rockets that gave them a speed of about 28,000 kilometers per hour, which is fast enough to be constantly falling around the Earth. That means the station and everything in it is weightless because of this constant freefall, and the station's high velocity ensures that it never hits the ground. The ideas we've discussed are all summarized by Newton's 3 laws of motion, so named because he enumerated them in his book known as Principia, first published in 1687. Newton's first law of motion states that an object moves a constant velocity if there is no net force acting upon it. That is why a spaceship, like the Apollo ship shown here on its way to the moon, needs no fuel to keep moving in space. Unless a force acts upon it, it will just keep going at constant speed in a straight line. Newton's second law of motion describes what happens when a force does act. The force causes an object to accelerate in such a way that the force is equal to the product of an object's mass times its acceleration. For example, when you throw a baseball, the ball accelerates as a result of the force your arm exerts on it. If you tried to throw a more massive object, like a shot put, the same force would give it a smaller acceleration. Newton's third law of motion tells us that for every force, there is an equal and opposite reaction force. This explains how a rocket works. A rocket engine generates a force that drives hot gas out the back, which creates an equal and opposite force that propels the rocket forward. These laws govern the motion of everything in the universe, and when combined with Newton's universal law of gravitation, they explain everything from the way objects fall on Earth to the orbits and motions of spacecraft, planets, stars, and galaxies.